This is the first of 3 videos in Chapter 20 dealing with heat and heat transfer. We'll look at thermodynamics and a historical background. Up until about 1850, thermodynamics and mechanics were thought to be different branches of physics. So they were not really combined until the work of James Joule, who demonstrated that there was a connection between the transfer of energy by heat thermally and the transfer of energy by work mechanically, and that the two could actually be, in a sense, equivalent in terms of energy. So energy was looked at to be generalized to include what is called internal energy, the energy of the state. And the law of conservation of energy emerged as a universal law of nature. James Prescott Joule, here he is. His experimental setup to the right here. Lived from 1818 to 1889. British physicist. Determined the amount of work equivalent to an amount of energy. And research led to the principle of conservation of energy. We can see his experimental apparatus here. And it's very, very nice, intricate design where you have these masses and they're suspended so that they have potential energy. As they fall, they cause the piston to rotate, and you have energy given into the water, and then the temperature changes as a result of that. So you have conversion of mechanical energy to the rotation in the water and the change in temperature. So heat and internal energy are actually different concepts. We can think of internal energy as being associated with the microscopic components of a system. As we go down the microscopic level, we need to look at the kinetic and potential energy of those components. Translational kinetic energy, the rotational kinetic energy and possible storage of energy, and vibrational motion in a storage of energy in the vibrational modes as far as the movement as that as well. So all that is associated with the internal energy of the state. As opposed to that is heat. Heat is the transfer of energy from one state to another. So it's not really the internal energy itself. It is the transfer of energy from one to the other, between a system and its environment, in particular because of a temperature change between the two. So one is an energy of state, the other one is a transfer of energy. So when we say we heat something up, we really, even though we may think of it as getting hot, the hotness is its internal energy, and the transfer of energy is the heating. The internal energy of a system can change due to a heat transfer or due to work. The internal energy can change even if no energy is transferred by heat. For instance, you can transfer energy by work. If you compress a gas with a piston, the molecules of the gas will move faster. As a result, they will heat up. And so the internal energy of that system will change due to the work that you added to that gas. So that's just work adding energy to the system. Mechanical energy of equivalent of heat. A calorie is defined as the heat required to raise the temperature of 1 gram of water 1 degree Celsius. James Prescott Joule determined this mechanical equivalent of heat to be 4.186 joules. So 1 calorie is 4.186 joules. Now a food calorie is actually 1,000 of these calories. A food calorie, as we talk about when we're talking about how many calories did you eat today, 1,200 calories today, that is 1,000 of these smaller calories. And hence, 1 food calorie is 4,186 joules. The British thermal unit, BTU, is the heat required to raise 1 pound of water 1 degree Fahrenheit. If I had 1 BTU, I would raise 1 pound of water 1 degree Fahrenheit, and on Earth, 1 pound of water corresponds to a mass of 454 grams. So that's 454 grams. 1 degree Fahrenheit is 5/9 of a degree Celsius. So I have 454 grams times 5/9 of a degree Celsius, which translates into 252 calories. So 1 BTU is 252 calories, or we can think of 1,000 calories as corresponding to approximately to 4 BTUs. So here's an example. Losing weight the hard way. A student eats a dinner rated at 2,000 food calories. He wishes to do an equivalent amount of work in the gymnasium by lifting a 50 kilogram mass. How many times must he raise the weight to expend this much energy? Assume that he raises the weight a distance of 2 meters each time, and that no work is done when the weight is dropped to the floor. So he's just going to raise it up, drop the weight, pick it up again. So he's not going to work against it as it's going to the floor, which probably would be a better workout, but he's not going to do that. So he's just going to raise it up, drop it, raise it up again. So he's going to raise it up, and each time he raises it up, it's going to be 2 meters. The work he needs to do is 2,000 food calories, which would be 2,000 times 4,186 joules per food calorie. So he needs to do amount of work equal to 8.37 times 10 to the 6 joules. Every time he raises it up, he's going to increase its potential energy by mgh. So that's the work he has to do that. And that's going to be the mass, 50 kilograms, times g, 9.8, times the height, 2 meters. And that work for every lift is 980 joules. So if he keeps on doing this, the number of lifts he's going to need to finally reach that level of energy is going to be the total energy, 8.37 times 10 to the 6 joules, divided by the energy per lift, 980 joules. He needs to do 8,540 lifts. This assumes a perfect conversion of chemical energy into mechanical energy, but in practice, the body's a little bit different. We should really divide this number by 6, because this will account for the loss of energy to heat, pumping the blood, circulation, that sort of thing. Hence, he would need 1/6 of this, 8,540 divided by 6, or 1,423 lifts. Still a lot of lifts in order to work off that one meal. Specific heat. Every substance requires a unique amount of energy per unit mass to change the temperature of that substance by 1 degree Celsius. The specific heat, little c, of a substance is a measure of this amount, and we can define it as being equal to the heat required per mass per change in temperature. And that will give us either calories per gram per degree Celsius or joules per kilogram per degree Celsius or Kelvin. So in SI units is joules per kilogram per degree Celsius or Kelvin. Historical units is calories per gram per degree Celsius. Here are some specific heat values for some common substances. If I look at water, it was defined to be, based on the calorie, 1 calorie per gram per degree Celsius. So that's really where we start. Water, pure water, has 1 calorie per gram per degree Celsius. Since a joule is 4.186 calories, or 1 calorie is 4.186 joules, then if we convert this to joules per kilogram, we have to multiply it by 1,000 in order to get it per kilogram. And so we have 4,186 joules per kilogram per degree Celsius for our conversion. Ice has half the specific heat of water, 0.5, and 2,090 joules per kilogram per degree Celsius. Steam is just about the same, half of that of water. So water in its solid form or in its gaseous form has half the specific heat it has when it's in the water form. And some of these other substances have lesser specific heat. So the largest specific heat of these common substances is associated with liquid water. Notice how small the specific heats are for these metals down here, and more on that in just a moment. The heat transfer, Q, between a system and its surroundings, based on this definition of specific heat, can then be written as mass times specific heat times the change in temperature. All we did was rearrange that last definition. So the heat transferred based on a change in temperature is the mass times the specific heat times the change in temperature. We can also write this as Q is equal to large C times the change in temperature, where this large C variable is called the heat capacity, and it's equal to the total mass of a substance times its specific heat. So that's the heat capacity of that particular object or that particular substance. So is the heat required to raise the temperature of that substance, whatever mass it has, by 1 degree Celsius. The heat transfer then is proportional to the heat capacity, and so if the heat capacity is large for a given Q, the change in temperature will be small, and likewise if the heat capacity is small, then the change in temperature will be large. So going back to our previous screen where we had the specific heats of all those substances, given a certain heat added to a substance, if it were water, which has a large specific heat and a certain mass of it, then its change in temperature will be relatively small for a given heat input. But if it were gold, say, which has a very small specific heat, then for a given heat exchange, the temperature change will be large. So if you have that same heat exchange to gold, then you try to touch the gold, it's going to be hot because the heat exchange will cause a change in temperature for that given heat exchange. Water has the highest specific heat of common materials, and this is partly responsible for many things we would see in nature, many weather phenomena in nature. For instance, water near the ocean water near the beach is responsible for maintaining a moderate temperature in those climates, because the water has a large specific heat. Hence, given any kind of heat exchange, its temperature change is going to be small, and whether it be a heat exchange out or a heat exchange in, cold or warm, in that sense, its change in temperature will be relatively moderate, relatively mild, and allowing it to kind of maintain the temperature in that region. It's also responsible for global wind systems and land and sea breezes, because say it were summertime and the ground were heated up more faster than the water, so you're going to have a difference in temperatures between the land and the water. Hence, as air is rising above the land, that's going to create a vacuum, if you will, as that rising air is going up, and the cooler air from the ocean is going to come in, and you will have yourself a sea breeze. Or when it cools off at night and the land is cooler than the water, then the same thing is going to happen in the opposite direction. The air is going to be rising over the water, and then you'll have a land breeze going out towards the sea. Calorimetry. A good insulator allows a thermal equilibrium between substances without any loss to the environment. If we had this kind of isolated system, then conservation of energy should apply And whatever heat is lost by one substance will be gained by the other substance. So the energy that leaves a hot substance will equal the energy that enters the cooler substance. Energy going into the cold substance will be the negative of the energy that is leaving the hot substance. Negative sign keeps our consistency in the sign convention. We'll actually look at this in a more general way in a moment. Sign convention of our change in temperature. Let's try this example. Cooling a hot ingot. We have a 0.05 kilogram ingot of metal. We don't know what it is yet. It's heated to 200 degrees Celsius and then dropped into a beaker containing 0.4 kilograms of water that was initially at 20 degrees Celsius. Now the final equilibrium temperature of the mixed system is 22.4 degrees Celsius. Find the specific heat of the metal. So we're going to put this hot ingot into water, and the whole system is going to raise temperature. Well, at least the water is going to raise to 22.4 degrees Celsius, and the ingot is going to lose temperature from 200 degrees Celsius down to the final 22.4. So essentially we have that the heat of the ingot, which is going out of the ingot into the water, plus the heat exchange with the water, which is coming into the water, heating it up, those heat exchanges add together should equal 0. One's going to be positive, one's going to be negative. So the mass times the specific heat of the ingot times the change in temperature of the ingot, which is our heat exchange for the ingot, plus the mass of the water times the specific heat of water times the change in temperature of the water, which is the heat exchange for the water, should equal 0. Now for the ingot, the final temperature will be lower than the initial temperature. So final minus initial for my change in temperature will be a negative quantity. So our heat exchange for the ingot is going to be a negative quantity. For the water, the final temperature is going to be higher than the initial temperature. Our change in temperature is going to be a positive quantity, and that heat exchange for the water will be a positive heat. Let's bring this heat exchange for the ingot over to the right. So I have a negative over there, which will be a positive quantity on the right. So I have basically the magnitude of one is going to equal the magnitude of the other, because we're going to, whatever we lose out of one is going to equal whatever we gain into the other. But this will keep our sign convention correct. We always think of a delta as being the final minus the initial. So the heat lost by the ingot will equal the heat gained by the water. So for the ingot, we have the mass was 0.05 kilograms, 50 grams. The specific heat of the ingot, we don't know. That's what we want to solve for. Our final temperature is 22.4 degrees Celsius. Our initial temperature is 200 degrees Celsius. We don't have to convert this to Kelvin because we're dealing with changes in temperature. And if we have changes in temperature, the change in temperature on the Celsius scale is the same as the change in temperature on the Kelvin scale. So we're perfectly okay using changes in temperature for this problem. Over on the right, we have negative the mass of the water, which was 400 grams. The specific heat of water is 1 calorie per gram per degree Celsius. So we're using 1. Our final temperature is 22.4, and we start with a temperature of 20. So that's going to be a positive change in temperature. Solving this, for the specific heat of the ingot, we have, as we divide both sides by this negative 177.6 times 0.05, we get that the specific heat of the ingot in calories per gram per degree Celsius, because that's what we use for the water, is 0.108 calories per gram per degree Celsius, or 453 joules per kilogram per degree Celsius. We'd have to multiply the 0.108 by 4,186. If I looked at this on that previous screen that had all the specific heats of common substances, I could identify this to be iron. So all these specific heats are intrinsic to the nature of the material, and I can actually use that to identify the material. In this case, the ingot is made out of iron. Okay, latent heat and phase changes. If we actually go through a change of form of a substance, that's called a phase change, and it requires energy to do that. The heat required to change the phase of a mass m is defined to be equal to the mass times the heat, the latent heat. And it could be the latent heat, which latent meaning hidden heat of the substance. The phase change could be from a solid to a liquid, in which case we would use the latent heat of fusion, or from liquid to solid, the reverse is true, the latent heat of fusion, or a liquid to gas, in which case we use the latent heat of vaporization, L sub V, or likewise from a gas to liquid. So that's what's involved in this phase change, is the heat either into or out of the substance to cause the phase change from one phase to the next phase. For water, which is what we're most interested in, the latent heat of fusion in SI units is 3.33 times 10 to the 5 joules per kilogram, which can translate as 79.7 calories per gram, and we possibly will just round this to 80 calories per gram for the latent heat of fusion for water. The latent heat of vaporization for water, as we go from liquid to gas, is 2.26 times 10 to the 6 joules per kilogram, or 540 calories per gram. So it's significantly greater. It's going to take a lot more energy to change liquid water into steam than it does to change, say, ice into liquid water. Here's how it might look. If I were to start with ice, cooler than absolute or than 0 degrees Celsius, it has a specific heat of 0.5, which is half that of liquid water itself. So I can, if I started with ice at say minus 30 degrees Celsius, I can heat it up much more rapidly than I could do, say, liquid water, because it has less of a specific heat, and hence for whatever heat I give it, it's going to have more of a temperature change. I heat that up to 0 degrees Celsius, and then I need to go through a phase change. So it will maintain itself at 0 degrees Celsius as we start melting the ice into liquid water, and that requires a latent heat of fusion to do that. So we go through the phase change, all taking place at a constant temperature of 0 degrees Celsius. Then we have, finally, liquid water, and then we can heat that substance up using MC delta T, and by adding a certain amount of heat, we can change the temperature of the water all the way up to 100 degrees Celsius, at which point we are going to go through another phase change as we go from liquid water into steam. That requires a lot of energy to do that. So at 100 degrees Celsius, at constant temperature, we start going through this phase change, which requires all this extra energy to go from water and steam. Finally, when we finally make the phase change, we got steam, and we can heat that up to higher temperatures if we wish. So we can see that most of the energy involved in all this graph of going from cold ice into hot steam, most of the energy required is going to be in that latent heat of vaporization when we go from liquid into the gas. Let's try another problem. A 40-gram block of ice is cooled to minus 78 degrees Celsius. It is then added to 560 grams of water and an 80-gram copper calorimeter at a temperature of 25 degrees Celsius. We wish to determine the final temperature of this system. And if not all the ice melts, and it's possible that it might not all melt, we want to determine how much ice is still left. So we have to do this piecemeal to figure out if we're in that situation. Remember, the ice must first warm to 0 degrees Celsius, melt, and then continue warming as water. So we're going to add this ice. Let's find out how much heat we need in order to raise this cold ice to 0 degrees Celsius so that it can go through a phase change. We need the mass times the specific heat of ice times this change in temperature. That's going to be 40 grams. The specific heat of ice we'll use as 0.5 calories per gram per degree Celsius. And we wish to change it 78 degrees from minus 78 up to 0. That's going to be 40 times 0.5 times 78, or 1,560 calories. We're going to need that much to do it. How much do we have? Well, if we were to cool the calorimeter and the water down to 0 degrees Celsius, that's the available heat. So let's see how much that is. We have the mass of the copper calorimeter, the specific heat of copper, and the change in temperature. So that's going to be the heat change of the copper. And then we're going to have the heat change of the water itself. So we have 80 grams of the copper. The specific heat of copper is 0.09, and we have 25 degree change in temperature. 560 grams of water. The specific heat of water is 1 calorie per gram per degree Celsius, and 25 degree change in temperature as well, as we bring both of them down to 0 degrees. This is a total energy of 14,180 calories available to warm things up. This is plenty to warm up the ice, because the ice only needed 1,560. So we're going to heat up the ice, and that's going to get all the way up to 0 degrees Celsius. That will take 1,560 calories, and what we have left after we take that away from the warmth that was available is going to be 12,620 calories left. We need some heat to melt the ice, so now we already have it at 0 degrees Celsius. How much heat do we need to melt the ice? Well, it's going to go through a phase change. 40 grams, about 80 calories per gram for the phase change for the latent heat of fusion of water. That's 3,188 calories needed to go through the phase change for the ice. We have that much energy available, so we're going to subtract that from this 12,620, and we still have available to us 9,432 calories. So the ice melted, and now that's water at 0 degrees Celsius as well. So now we have the copper calorimeter, the water that cooled down to 0 degrees, and the water that heated up to 0 degrees, went through a phase change. Everything is at 0 degrees Celsius now, and we have left over this 9,400 and forget what it was. 9,432 calories was left over. Now we want to heat everything up from this point up to some final temperature. So we're going to heat up the calorimeter at 80 grams at the specific heat of 0.09 calories per gram per degree Celsius for copper. And that's going to go through a change in temperature to some final temperature minus 0. And do the same thing for all the water, the 560 grams plus the 40 grams that we now have. Specific heat of water is 1, and we're going to go through the same change in temperature to some final equilibrium temperature. So we're going to solve this for delta T. Delta T will equal 9,432 divided by 7.2 plus 600. We're going to have a final change in temperature of 15.5 degrees Celsius. And since this is our final temperature minus 0, that will indeed be our final temperature, 15.5 degrees Celsius. So in actuality, the ice cube will heat up to this point, and the calorimeter with the copper and the water will cool down to this point. And that will be the final equilibrium temperature of everything, 15.5 degrees Celsius. Supercooling and superheating. Here's supercooling. Say we start with Superman. The process by which Superman becomes with it is what we call supercooling. So if he becomes with it, cool man, he is super cool. No, supercooling has something to do with water. Let's say you were to cool water and you cooled it below 0 degrees Celsius without freezing it. This is possible if you don't have nucleation sites and if you don't have imperfections in the water that allows ice crystals to form. So you cool it fast enough so it doesn't have a chance to freeze, and you have yourself a supercooled water. And it might be just waiting for disturbance such that it will freeze up. You probably have seen videos of this on YouTube where you have a liquid and it's just ready to find something, a reason for it to freeze. It's below the point where it should freeze, and it's just ready for a disturbance of some sort to cause it to suddenly freeze. We can also have superheating. You can raise water to a temperature greater than 100 degrees Celsius without boiling it. This is called superheating. And the formation of a bubble of steam needs a nucleation site for that to occur. So it needs some kind of imperfection, either a scratch in the container or some kind of impurity in the water. Via pure water and a real good container, you can superheat it to the point where it actually doesn't yet form the gas, but it's ready to go. So any kind of disturbance in that, you disturb that superheated water and it could explode as this water suddenly starts changing to gas and it is doing it uniformly. So you have an explosion as this superheated water becomes a gas. The bubbles will immediately form and become gaseous, forced out of the container. Superheating. All right, this is the first of the 3 short videos in this chapter 20 on heat exchange.